All right, there we go. So we are recording and everything. So here we go. This is what we were talking about last time. We had previously talked about this idea of a scalar surface integral, right? So if you're computing mass as a whole, which is the sum of the parts, or something like that, or if you're computing the moment of inertia, which is an integral set up by a more sophisticated argument, but nevertheless just an integral. If you're computing these kinds of things where there are scalar quantities that are ultimately what you're interested in, and scalar quantities that go into computing them, then yeah, sure, cool, no problem, it is what it is. But if you're interested in computing flux, right, defined by this formula right here, for good reasons, right? Flux computes important stuff for us, right? Then what you find is that there's something intrinsically oriented about it, right? So if the fluid is going that way, well, if that's what you consider to be the positive direction through the surface, then you're going to get a positive little bit of flux there. But, I mean, you could just as well say, I view this surface as being oriented downward. Downward is what I'm interested in which case on this piece, now you've got a negative piece of flux, right? The mass doesn't behave that way, right? This is an intrinsically oriented situation. So we had to basically, we had to adapt our idea of what a surface integral could do to allow for this orientation, and if only for the contrast purposes of it all. I like to call this a vector surface integral to emphasize that we're talking about what's really ultimately a vector valued integrand, and of course likewise a vector differential. And it really is importantly different construction, and we should denote that with our favorite notation, and I think also with our terminology. Okay, so we wrote down some formulas last time. I did plant a thought of, wait a minute, what is the problem with this little bit last time, right? I mean, if it looks like a duck and quacks like a duck, is it a duck? Maybe it is, maybe it isn't. We have to worry about that for the next few seconds. But that said, other than this business about ducks, look at this. We can compute flux now with vector surface integrals. You want to compute a flux of this vector field over a certain surface. Cool. Flux. We have that formula, right? And there's a certain amount of chugging in this plug and chug, but so you do have to parameterize and take the partials and take the cross product, right? And then you got to do the pullback. I mean, there's several little steps there, but anyway, doable. Okay, so let's confession time. What is the purpose of that asterisk? Why did I want y'all to worry about that a little bit? And here we go. Comes up in this question of, does the parameterization matter? And the answer is actually, yeah, kind of. It's a little bit surprising. Here's the point. Recall we have this picture where if you have a surface, not just a surface, an oriented surface, right? If you're going to talk about flux, we have to have a decision on which direction. Is it that way? Is it this way? Which direction is the positive direction through the surface? It is perfectly legitimate to orient this surface in either of those two ways. Right? There's no law that says up has to be the positive direction. By the way, what if your surface is like this? What if your surface is a vertical thing? There is no up, right? So there's no sort of canonical choice on how you orient a surface. Whatever choice you make, again, we've already given a name to. It's the orientation unit normal. Okay, now that said, how do we compute this? Well, we've got to parameterize our surface. When you parameterize, there are certain consequences. That tells you which direction your XS is going to point. It tells you which direction your XT is going to point, which tells you which direction your capital N is going to point, which tells you what I'm going to call parameterized unit normal will be. That all comes out of the parameterization. And here's the thing, when you're parameterizing surfaces, look back at all the parameterization techniques that I showed y'all, right? None of them have a recognizable, like which direction does that parameterization's normal go, right? It doesn't leap off the page at you. Look back at all those techniques. It's just, this is just how to make the points functions of S and T, and we didn't say a word about the direction, capital N. So it's a coin flip. There's a significant worry here, right? It could be that maybe this is your orientation unit normal, and then you parameterize so that this is your parameterized unit normal, and then look at that. Those are the same, right? Those point the same direction through the surface. So you could get lucky, accidentally, inadvertently parameterize it the correct direction, right? But it's a total coin flip because, again, as you were parameterizing, you weren't paying attention. You kind of can't really pay attention to which direction your orientation unit normal is pointing. It could be that you were supposed to parameterize that way, but you accidentally parameterized that way, and now you're off. Now you've got the wrong direction. Everybody see the problem, the worry? What are the consequences of that? And by the way, just to clarify the asterisk on the previous page, here's the math crime confession. When you write down this formula, the unit normal vector here is the orientation unit normal. That's the unit normal that you were supposed to pick. That's what comes from the definition of the oriented surface that we're dealing with. Right? Whereas once you compute once you do your parameterization and compute the blah blah blah, and eventually you've computed your capital N vector, well, that direction is the parameterized unit normal. And so again, coin flip as to whether these are the same. In this case, as I have it drawn here, these are not the same. And so what we have is, I guess you could say, it looks like a duck and quacks like a duck, but it swims under the water instead of over the water. It's a weird, it's an opposite duck, right? Right? Anyway, that reasoning just didn't quite hold water. Anyway, yeah. How we doing? Okay, so if we do get it backwards as a coin flip, we very well might. Notice that just means our normal vectors that we're using, they're just exactly the negative of what they should have been, which means every single term in our integral is off by a minus sign. That means that my result will be off by a minus sign, and I can fix it with a minus sign. Simple as that. Okay. All right. Now you may recall back in chapter 6 here, we talked about that the parameterization has to go the correct direction, and if you parameterize wrong, right, your vectors or your dx vectors are backwards, and you're just off by a minus sign. Right, and we developed a notation and documented this as a theorem, and then just realized that, if you parameterize backwards, just insert a minus sign to fix it. And we're going to do the exact same thing over here now in chapter 7. Okay, so let's see an example of this in action. How is this going to actually play out for you? Here is an example. Very, very similar to an example we already did. You might even recognize that vector field and this surface. Same surface, same vector field. I did change it in one little way. This I've indicated here is oriented downward, right? So this surface oriented specifically downward. Now that's in the statement of the question here. By the way, real quick, you will notice this is not the way it was in the previous version of this question. In the previous version, it was oriented upward. In fact, in this previous version, I kind of completely ignored orientation altogether, right? So that's another little planned math crime for which I now confess, right? We didn't even think about the orientation here, but we're going to think about it here. And here now we're going to start. The way you're going to handle this is you're going to start these questions not even worrying about orientation. To start, use your graph parameterization or whatever your favorite parameterization method is for that problem. Just parameterize it. Don't worry about orientation. Take the partials. Don't even worry about orientation. Take the cross product per usual to get your capital N vector. And now is the time that you have to pause. You can't just proceed with the plug and chug like I did with that last example. Now is the time to take stock. Now is the time to worry. Okay, well, the surface came to me oriented downward. It says so right there. I've parameterized this thing to get my capital N vector, and I can see with that z coordinate, right? I mean, obviously it doesn't point exactly upward, but it's definitely not pointing downward. Right? This capital N vector is like, I don't know, like about like that or something, somewhat upward. We were told to orient it downward, so we should have oriented it like this. We're off by a minus sign. So we just have to recognize, whoopsie, right? I parameterized it upside down. And then we fix that by just inserting a minus sign and you're going to need to put some little comment in here. You don't have to write, a whole paragraph. You can just say, maybe here. Let me delete. On an actual question, you can just kind of do like that, and then say, "Oops." Right? This gives a clear communication that you're comparing that with this. That is the indication that you've parameterized it the wrong way. We see here that we fix it with this minus sign. Note how little documentation that requires, right? And we fixed our result, and off we go. Everybody happy? Okay. Now I do want to give you a warning. It is easy to fix. It's also easy to fix it the wrong way. Let me show you what a lot of students do. This is not okay. You got to be real careful not to do this. Now, first thing I'm going to do is I'm going to highlight this question, right? The question that was asked was compute flux. That came with the given orientation. This integral here uses the ds vector, which is defined based on the given orientation, right? And now, down here, let's look at this integral. That integral, you can see right here, right? That integral right there is in reference to the parameterization. Capital N comes from the parameterization. So this is the integral that's different. And then, of course, every integral that follows is also different, right? So this came out of the parameterization. So that means the minus sign has to go here, right? Because the green integral and the blue integral are not equal to each other. They are literally negatives of each other, as we observed. Does that make sense? So here's what a lot of students will do wrong. In some form or another, students will insert their minus sign, let's say here, but not have a minus sign over there. but not have a minus sign there. This is a problem. Now, there is a temptation to say, well, yeah, look, but the minus sign, it got its way in there. This is going to lead to the correct result. Right? But if you listen to that counter argument, poo-pooing my complaint here, notice the focus is on the answer. Right? And again, that's not what this class is about. This class isn't about answers. This class is about reasoning, the concepts, demonstrating understanding of proficiency with the important ideas of the course, right? And as this is written right here, this is not okay. Let me point out the beefs that I have with this. As written here, as adjusted here, this student is claiming that blue integral is equal to that green integral. That is not true. That's a problem. Right? Mathematicians are real uptight about having false statements on the page. Right? So that's a problem. And then here's another problem. Look at this. This student has written down a suggestion that this blue integral is the negative of itself. Again, not true. That's a problem. Does everybody see what I'm talking about here? I mean, so if you insert the minus sign, kind of, who cares where you insert it? It's going to get you the same answer anyway. Yeah, that's not what we do here, right? You have to insert the minus sign appropriately to make sure that your reasoning doesn't have, as per the way I have it highlighted here, two mistakes in it that happen to cancel each other. So, canceling errors are still errors. So anyway, keep that in mind, right? I know it's a hard sell and a heavy pitch, and I know all your high school teachers may have told you different, but they're wrong. How are we doing? Yes?
Could we put the negative in the end and fix it like earlier, or that kind of...
No, if you want to have a bunch of true statements on the page, that if you want your argument to be valid, then no. Yeah. Now, I suppose one thing you could do is if you say right off the bat, I'm going to compute the negative of the requested flux by orienting this the wrong way, and then just have the entirely 100% wrong calculation followed by, as previously discussed, I oriented this upside down, and so therefore, then yes, right? But the point is you have to explain what you're doing. Because if you say, without explaining what you're doing, if you write this down false, it's wrong. And again, we can't have wrong statements. Yeah. Does that make sense?
Yeah.
Okay. Okay. The most extreme example of this, by the way, and I point this out just for dramatic purposes, but what I see some students do sometimes is to have a calculation where they end up with -6 as their answer, let's say, and then they realize in their head, I forgot a minus sign somewhere, and then they just say equals 6. You can't do that, right? You can't say -6 is equal to 6. It absolutely 100% is not. So I hope everyone can see why this is unacceptable. And again, I'm perpetually mystified that there are teachers, especially in high schools, that will allow this obvious nonsense. So anyway, all right. I've spent too much time on my soapbox about this, so I'm going to proceed now. Okay, now let's talk about the language. You got to be a little bit careful with the language. It is a slightly complicated story as to how to talk about orientations. How, for example, if I have this surface, if I have this surface right here, and I have these two possible orientations, right? There's this orientation like that in green, and there's this orientation like this, highlighted in blue. How would I describe these two orientations? And one thing you could do, which I don't think we want to do, but one thing you could do is you could write out an explicit formula for that tells you what the chosen orientation unit normal vector is explicitly and exactly everywhere on the surface, and that sounds like a lot of work. I don't want to have to go to a bunch of trouble and commit to a bunch of work just because I want to communicate a choice between two things. Right? This is a much simpler matter on the asker's end. Look, I just need to distinguish between green and blue. I mean, it's your problem. The person who's going to answer the question is the one who's responsible for computing stuff, right? The person asking the question just needs to distinguish between these two options. So, upward versus downward, you could quibble and point out that, well, those vectors don't point exactly upward, do they? They're not straight up vertical. Well, of course they're not. They have to be perpendicular to the surface. The surface isn't purely horizontal. Obviously, the normal vectors aren't going to be purely straight up vertical. So the point here is that you have to interpret the language not as exact, but as unambiguously choosing between two options. Right? And if you look at those green vectors, every single one of them is somewhat upward. And if you look at those blue vectors, not a single one of those blue vectors is in any sense upward. So when we say upward, there's no ambiguity remaining. Obviously, we're talking about that green orientation picture that I have there. Obviously, we're not talking about the blue one. Right? So note the purpose of the language here is not to be exact in its description of the normal vectors. Its purpose is to be unambiguously communicative of the choice between the two. So that's the goal. Now, how you use the words to accomplish that goal, I mean, I guess you could say inward versus outward. You'll notice that I have a little right? I mean, I guess you could do that. That's kind of okay. I will point out that technically there is no inside. There is no outside. So I don't, right? It gives me the willies a little bit right now. That said, I mean, I don't think anyone would see the word inward here and guess wrong, right? Nevertheless, it's a little suboptimal. So you want to think carefully about your language and try to pick the best choice. Notice that upward versus downward, while it works great in this case, it doesn't work at all in this case. Down here, right? If you look at this surface, this surface here, and we've got these normal vectors like so, and we've got we've got these normal vectors like so. Some of the green vectors are up, some are down. Some of the blue vectors are up, some of the blue vectors are down. Upward versus downward just doesn't communicate at all. So in this case, we wouldn't use that language. In this case, we would very happily go with inward versus outward. The green vectors are all pointing inward. Inward is pretty clearly defined here. None of the blue vectors point inward. You see how this works great. Is everybody happy with there's kind of there's a touchy-feely aspect to this. But just keep in mind, the goal is that the language remove the ambiguity, not that it precisely, formulaically describe the vectors. Okay. All right, that's enough of this. Okay, so sometimes you get lucky. Now I'm going to point out this is something that we saw with vector line integrals. Sometimes you get lucky with the geometry, like in this case. And check it out, our dx's were that way, our forces were always that way. They're always perpendicular, dot product 0. You got to love it. And, that kind of thing can happen with vector surface integrals, too. So, again, here, got some vector field. All right, we want to compute the flux, and now I'll tell you what a lot of people would do, very reasonably. A lot of people would say, oh, I'm going to use the spherical graph parameterization. You write down your spherical graph parameterization. There's trig everywhere. You compute the partials, you compute the cross product to get your capital in, and you plug and chug in the pullback parameterized way that we've been talking about. You could do that, but there's trig everywhere, and you're going to have a ton of trig, and your integral, and it's got the potential to get weird. Right? Half-angle formulas, and I don't know. It's doable, but could be hard. So the clever observation to make here is that you don't have to parameterize. What you can do is just look right at your picture and say, well, I was told my surface is a sphere. I know what the normal is going to be. It says oriented outward. I can just write down exactly that picture of this outward oriented normal. By the way, we love spheres. The point describing my position, keeping in mind that I can view that by the corresponding position vector, also perpendicular. So these are parallel, and I know the radius is 3, so you can straight up just write down a formula, a little bit of geometry arguments. You could just absolutely write down a formula for your orientation unit normal right there. And then just plug that in. No parametrizing, no partials, no cross product, no resulting trig in my integrals. It's pretty sweet. Right? Everybody with me? Okay, and so what did that buy me? Well, then, again, you can crank out this dot product 0, integral 0, drop the pen, walk away. No fuss, no muss. So how often does stuff like this happen? You'd be surprised. The world is full of conveniences and symmetries. It's very nice, right? Not everything, not even most things, but very often stuff like this, super handy. So please do always be on the lookout for it. Here's another version of that, basically that same idea. Let's see here. Let me expand. There we go. Basically the same idea here. Now we are told to look at this plane, y equals 3. Specifically, we're told to look at the part of that is kind of inside of this vaguely circular, but importantly not quite circular curve inside of that plane. Right. We're given an orientation direction, so oriented in the positive y direction. And now let's just think for a quick minute here before we get into the plug and chug of it all. I'm looking at a surface that's sitting inside of a flat plane. That means that my surface is flat. It's got a weird edge to it, but the surface is flat. And the perpendicular direction to a vertical plane is horizontal, and says right here, choose the positive y direction. So again, I can just write down my unit normal thing. Boom. That's an awesome little bit of convenience that, again, comes out of thinking about the geometry of the scenario that we were given. Is that cool? Everybody with me? So again, looking at the integral down here, I get to just immediately say, oh yeah, that little n, I get to just write that down. I don't have to mess around with the whole parameterizing and capital N and the computation, etc. Okay, not that would be hard in this case. Now notice another thing. In this entire surface, for my whole surface there, I am inside of that plane y equals 3, which means y will be 3 for every part of this calculation. And notice that if y is equal to 3, right, then this expression right here, the second coordinate of my vector field is just going to be 0. And that means I get to write that down right there where my vector field went. Right, my vector field goes here. That second coordinate of the vector field is 0. Again, where did that come from? Came from heads up looking at the geometry and interpreting accordingly from the geometry. Doesn't come out of the algebra particularly. It comes out of the geometry there. Everybody cool? Everybody with me? So what is all of this by us? Well, in this case, again, it kind of all comes together, and lucky break, this dot product is 0, therefore the integral is 0. And drop the pen, walk away. Okay. Happy? All right. Okay. Whoopsie. Moving along. Let's see here. Coordinate surface integrals. Wait a minute, that sounds familiar. Didn't we talk about coordinate line integrals when we were talking about? Whoa, I hit the wrong button there. Sorry. I meant to hit this button down here. Didn't we talk about coordinate line integrals when we were talking about vector line integrals? And remember, we had this little kind of rewrite of our vector differential that ultimately just gave us this alternative notation for vector line integrals. Well, guess what? The exact same, morally same thing happens with surface integrals. Your vector differential, ds instead of dx, but still vector differential, blah, blah, blah. Actually, you know what? It's a little more than that, isn't it? Blah, blah, blah can be rewritten with respect to coordinate differentials. The punchline of which then is that gives me now an alternative notation for how to write vector surface integrals. If you find yourself with a vector surface integral like so, you could instead write it like that. And again, the analogy is very strong. That's why I'm leaving the analogy up here on the screen. Very strong analogy. It's a little bit different in how certain bits of the action go down. Let me go back to here and let's take a look at, for example, how did we deal with this thing, and why am I just calling that dy dz? This is a little bit of an eyebrow raiser. As we've noted previously, this is the formula anyway for a two-dimensional change of variables, even though we are not really seeing a two-dimensional change of variables in the picture. So it's a little strange, but that said, if we get comfortable with the idea that, again, there's kind of a faux cancellation there. It's not real. It's not a real cancellation. That's not a fraction. These are not independently defined things. But we've seen multiple versions of why, even though it's not a fraction, it behaves like a fraction. And if you just kind of say, well, it seems like this reasonably ought to kind of sort of cancel, then wouldn't it seem reasonable to call this dy dz? And if we were doing a two-dimensional change of variables, that absolutely would make sense. And in a sense, we kind of are. Now, again, if you're interested, if you want to come to my office hours, and I'd be happy to flesh this out. There is a great geometrically natural way to view this as literally being a two-dimensional change of variables. Those of you who came and talked to me about that previously may see what I'm talking about. But anyway, if you're interested, come talk to me. Happy to do it. Otherwise, I'm going to say we're just going to rewrite these like so. That's... we didn't really have that issue with vector line integrals, coordinate line integrals. The issue didn't really come up. But everything else is pretty analogous. So again, we find ourselves in this situation where we have this choice. Which one of these notations should I use? This one has a natural aspect to it. The vector field is something physically natural. The ds vector is, I'm going to say, geometrically natural in a clear way. It's perpendicular to the surface. It represents the size of each little piece, right? It's a natural thing. Whereas, by contrast, what's dy dz? Right? What is that? How am I supposed to see that in the picture? and there's an answer, but it's we don't have time to deal with it. Certainly, though, I think it's harder to make geometric sense out of it, and there's the little matter of it's quite a bit bulkier to write down. Okay, so in Math219, I expect and assume that most of us are going to prefer that notation, and I'm not clear why in Math219 we would make the choice to use this notation unless we had to, unless something, every so often it happens to be convenient. Okay, that said, just like in the previous section, this, frankly, is kind of what differential forms look like. Not exactly. It's missing some, a key aspect, but this is very reminiscent of this very powerful, important, natural thing called differential forms. That is, it's really the answer for a more sophisticated conversation about this material. So this is not a bad idea. It's just not useful for us, right? But I want you all to be aware of it. You are going to see it. This notation is in common use, either by people who do use those sophisticated ideas or by people who like those sophisticated ideas and use this notation accordingly, right? So you're going to see it. It's out there. It's in your future, and you need to know what to do with it. And my advice is that when you see something like this, to recall that these coordinate differentials they are part of your ds vector. They are coordinates of your ds vector. Very critically, in that order as written. And therefore, their sort of scalar integrands, if you will, those are just telling you your vector field. So, if you see something like that, and if you feel it necessary, as you might, then you can sort of reverse engineer what the vector field f is and rewrite that whole thing as integral f dot ds. Okay, symmetry theorems. And, well, that was the very next thing we talked about when we were doing vector line integrals. It's the very next thing we're going to talk about here with surface integrals. Good news, bad news. Let's see here. Where did my colors go? You know what? I'll just deal with it as is. But recall we had this theorem for scalar line integrals, specifically scalar line integrals. Yeah, odd symmetry theorem, just like you would have figured. And good news, ditto for scalar surface integrals. It's exactly the odd symmetry theorem that you would hope for, just like it was for double integrals and triple integrals and single variable integrals, frankly, and scalar line integrals. So if you have an odd integrand and a symmetric domain, both conditions apply, same linear plane of symmetry for both requirements, your integral 0. Gotta love it. And we have the same warning. So this is not, well, you know what? It does not work for vector line integrals, right? So it didn't work. The unit tangent vectors were pointing the wrong way. And very analogously, for vector surface integrals, it does not work. In this case, it's a little bit different, but you see the analogy is quite strong. Right? Again, it's very, very similar. That's why I deliberately wrote it out in analogous ways. But let's get back over here where I can focus. Why doesn't this work for vector surface integrals? Well, it's, again, because of the orientations, not tangent vectors, like vector line integrals, but our orientation unit normal vectors that are, kind of hidden inside of our ds vectors. They're not the same as each other. They're not opposite of each other. They're just different. The relationship between them is not convenient enough to resurrect any sort of odd symmetry theorem. So please, it's very important, do not try to make an odd symmetry argument for a vector surface integral any more than you would for a vector line integral. They just don't work. It does remain, conveniently, let's get rid of all of this, that if you find yourself looking at a vector surface integral, and if you rewrite that vector surface integral using that notation, and if now, and I'm going to have to zoom in just a touch here, if you do reinterpret then with the normal vector dot product included, if you interpret that as being a scalar integrand with now a scalar differential, thus interpreting this now as a scalar surface integral. Forget about where it came from. If you just think of this now as being a scalar surface integral like so, and if that integrand, not your original vector field, but f dot n, scalar valued function, if that is odd, and if your domain symmetric, then yeah, absolutely, of course, that's perfectly fine. But you do have to do the work and reinterpret it correctly, of course, as a scalar surface integral. How are we doing? Is everybody okay? Okay. All right. This next page is kind of unexpected little summary of strong analogies that we've seen some of. We've talked about some of the analogies between vector line integrals, vector surface integrals as we've been moving along, but I want to kind of bring it all together here, all in one location, just to emphasize how strong the analogy is. And I emphasize this is weird because if you look at where did we get vector line integrals from, well, it was because we were interested in this physical quantity called work. That's where vector line integrals came from for us. And if you look at, on the other hand, where did vector surface integrals come from? Well, it came from this physical quantity called flux, which really isn't work, is it? It's a really different physical thing. We were looking at two very different physics problems. So you wouldn't immediately expect these two different constructions that came from different questions to look a lot alike. But let's take a moment to dwell on how much they really do look a lot alike, as it turns out. So you can see I've got a curve here, and I've got my usual players in the conversation about how to define vector line integrals, right? We've got our parameterization, we've got our sort of t-axis, that's the pullback space, that gives you a velocity vector and a unit tangent vector, blah blah blah, all that. Those are our usual players for vector line integrals. And okay, well now here is our playground for vector surface integrals. Again, our surface, you parameterize and take various derivatives and blah, 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 capital N and all the various players in C. Okay. So let me point out how the players on the left and the players on the right, they pair up in extremely natural, analogous kind of ways as follows. Okay. Let's see here. I'm going to try to make good color choices so this will show up well. We have our velocity vector on the left. Our velocity vector may or may not point the right direction, right? If you parameterize backwards, it's going the wrong way. But anyway, so that's just a question. But your velocity vector is, again, part of it participates in those equations. It's the thing whose magnitude is the speed, which ends up being the stretching factor. All right, well, check it out. Over here on the other side, we have this capital N vector. And where did capital N come from? It came from derivatives of your parameterization. That's where V came from. V was the derivative of the parameterization. And check it out, it too either is or isn't pointing in the correct direction, depending on which way you parameterized, and it too is the thing whose magnitude is our stretching factor. Whoa, weird. Right? That's surprising. Two different questions, and wow, that's an oddly strong analogous role between V and capital N. In both cases, we have a unit vector version of those, which go here and here. How about that? In both cases, we talk about the size of the little piece of curve over here, area of the little piece of surface over here. Right? In both cases, those sizes show up in analogous ways in the algebra. And in both cases, I can take that size, length for the piece of curve, area for the piece of surface. I can take the sizes, I can multiply by the orientations, and infer the vector differentials, dx on the left, ds on the right, that fit in like so. And I think that is shocking. Two totally different stories, completely different players. The analogy is off the charts, right? I mean, isn't that weird? Now, why am I showing you this? Why is this worth class? And by the way, you can, if you have the time, you can entertain yourself by looking at the following subsequent formulas on the left and the right, sort of different ways of writing down the resulting integrals. You can take these players that I've color-coded up there, color-code accordingly down in the integral equations, and the pattern, again, perfect. So, super weird. Okay, why am I showing you these things? There's two reasons. First of all, this is what I like to call a cultural point. Again, math is not just about getting to the answer, right? Plug and chug, turning the crank. We have computers for that, increasingly. By the way, you may recall I talked about that exact point on the class website, right? In some places, right? If what you bring to the table in a situation where math is needed, such as a future job or a future graduate position or something like that, if what you bring to the table is that you can do plug and chug, yeah, we have a computer that does the plug and chug. They don't need that, right? It doesn't help. Right? What you need is to understand the ideas, and so there, I think it's valuable, even if you don't see the bigger theorems. Right? Of course, you're not going to see the bigger theorems that we don't have time to talk about. It's too sophisticated. It's just not appropriate for this class. But you can see glimpses of evidence that these constructions must actually have something very strong in common, because here's the sort of the evidence. It is extremely analogous. This can't be coincidence. These must be deeply related in some way that we just aren't seeing, right? So knowing that that's true, I think is just that's valuable cultural knowledge, right? And it's a good thing to know what's out there, even if you don't really know the details. The other thing is, I think this is good for learning formulas, and it's good for helping you learn ideas, because, for example, you might find yourself trying to learn, all of this business about vector surface integrals, and maybe you get sort of stuck on, why do we need to understand this capital N thing, right? What's the purpose of capital N? What role does it play? Well, you look at this analogy, and then you can say, okay, well, apparently it's playing a role kind of like the velocity here, and that can help you kind of make sense out of what capital N is doing, and it can help you remember the corresponding formulas. N and V play analogous roles, and that can help you remember that, like V, N is the thing whose magnitude is your stretching factor. Patterns make things easier to remember. You know what I mean? So anyway, I think there's value in that as well. Okay. All right. Plus, it's just surprising and cool. That's kind of back to the cultural point. Okay, so that does 7.2. We're going to move on now to 7.3. But before we do, we're going to very quickly flash back to Chapter 6 here, and I want y'all to remember this discussion we had before we got into Green's theorem. Right, we had this discussion here about what is a quantity, what specifically is an accumulating quantity. Right, so the whole is the sum of the parts. Not every expression, not every quantity has this feature. A lot of physical quantities do. Some geometric quantities do. But in general, this is not a universal feature. Some things, the whole is the sum of the parts. Some things simply, no, it isn't. And this feature of being an accumulating quantity is bonkers useful. And now, again, I made this argument in the two-dimensional context, and then subsequently I just kind of claimed that there is a sort of a three-dimensional volume version of this, and that's what we're about to see here. So please interpret these results on the left in the kind of the three-dimensional volume sense. But if you have an accumulating quantity, then you can think of that as a kind of like a physical stuff. It's as if it's a substance that's distributed over the area, even if you don't compute it that way, even if you don't visualize it that way. It behaves that way. It behaves just as if it is a stuff distributed over that interior. And as such, you can talk about the associated density that you can use, and the way we use densities. There is the resulting, what I like to call accumulation theorem. The whole is the sum of the parts, and the parts are computed with densities. Powerful results all come out of one property, right? If you have an accumulating quantity, you can do these things. Okay, so again, I just want to make sure we're clear on that idea. And so now we go back here to where we were in Chapter 3. I'm going to have to define a couple of things, but we're about to encounter an accumulating quantity. And therefore we can make all of those conclusions about stuff and densities and integral theorems. Okay, so all right, so just keep that in mind. That's just a little foreshadowing. Here we are, by the way, in section 7.3. This is another giant section. I don't know why the author likes to have these massive, giant sections, and some other sections that are teeny tiny, itty bitty, have one little idea in them. But anyway, that's whatever. It's going to take us probably all but the last day of class to finish up this last section. It's a huge one. Okay, so starting off, let's talk about Gauss's theorem. Gauss's theorem is going to involve boundary surfaces. Boundary surfaces are pretty much exactly what you think they are. It's the surface that is the boundary, right? I mean, I think we all know what boundaries are. It's the dividing. It's sort of where the border is between where the set is and where the set isn't. Right. So you can see what I have highlighted in green here. This is, by the way, my attempt to draw a kind of a hollowed out. Imagine a lump of clay that has a air bubble in the middle of it. Right? You can imagine such a thing. So what I have in green there then is the boundary. of that solid. Everybody on board? Three-dimensional, right? We're in 3 dimensions now. Okay, so the new concept is that this word boundary now and henceforth in the rest of this chapter is a loaded word. Boundary means 2 things. It means, it's the border. It's the dividing border between set and not set, sure, right? But with a specific orientation. This is now intrinsic to the word boundary. Boundary means oriented in a very specific, prescribed way. Now, I'm going to mostly gloss over the speech I gave previously when we were talking about Green's theorem and stuff like that, and I point out, yes, the convention on boundaries is arbitrary. It is arbitrary. It was kind of a coin flip in some sense, but it is now highly standard, and so even though it is arbitrary, it is absolutely the standard, and so it's not an optional kind of thing, so we got to stick with it. Here is the rule: away from the solid. That's the rule. Right, at any given point on the boundary, keep in mind the boundary's job is to be the border in between set and not set. So there's wherever you are on the border, there is toward or into the solid, and then there's away from, out of the solid. So our convention is away from the solid. Notice that doesn't always mean outward. Sometimes away from the solid means inward, as per that piece of the sort of the inner border, the bubbles border, if you will. Is everybody on board? Everybody see the geometry? Okay, with that in mind, here's our accumulating quantity. Again, I just, 5 minutes ago I gave this whole speech about how accumulating quantities, that's the thing, that's what's going to allow us to make big theorems. Here it is. Boundary flux. Believe it or not. Doesn't seem like this ought to work, but boundary flux accumulates over volumes. The whole is the sum of the parts. Really feels wrong, but it works. The whole is indeed the sum of the parts. So, for example, let's here's a lump of a solid, and here's the boundary of the whole. Which now, keep in mind, boundary of the whole oriented following the rule, oriented away from the solid. That's the boundary with orientation of the whole. Fine. Okay, now let's look at the parts. There's this kind of part over here on the left, and its boundary is away from the solid, away from the lump R1. And then there's the bit on the right over here. There's this thing, and again, oriented away from the lump, away from the solid, away from R2. So there's that. Now we ask open-mindedly, even though it doesn't look right, is green plus blue equal to purple? And it doesn't look like it is, because look at all this stuff in the middle. I see a bunch of green and blue, but no purple for it to pair up with. Right? And so I can kind of erase, well, here's the, let's get rid of the parts where they obviously pair up and cancel, right? So clearly on those pieces we have a match. But what's going on with this right here? Well, that is two fluxes, both computed on that same shared face, one oriented one way, the other oriented the other way. Same integral, opposite orientations, they cancel, and once they cancel, there's nothing left. The whole is indeed the sum of the parts. Everybody see how that plays out? Doesn't that look really familiar? Isn't that morally kind of exactly the same picture that we drew when we were talking about Green's theorem, right? When we were talking about Green's theorem, we had a shared edge in the middle, oriented in opposite directions, and so they cancel. Same thing. Just three-dimensional and, perpendicular to the surface instead of parallel to the boundary curve, right? It's geometrically a little different. But then, now a reminder, when we think about flux through a curve, right, we made this observation that you can think of the two-dimensional divergence theorem as, again, flux through. Let's see here. Let me get the thing. There we go. Flux through. And these two pictures really are super analogous. When we were looking at the 2D divergence theorem, we could view it as an accumulating quantity through the boundary curve. Here we're looking at flux as through the boundary surface. Really, really analogous. It's the same fundamental idea, frankly. Let's see here. Okay, and then I need to, how do I, oh yeah, this one. Okay, there we go. Okay, so we have an accumulating quantity. We already have huge ideas of what we can do with accumulating quantities. We can view it as a kind of a stuff. Behaves kind of like a stuff. It's hard to see the picture, right? It doesn't leap off the page as a stuff on the interior, right? We think of boundary flux as happening on the boundary. How much of the boundary flux here is actually happening on the surface of that little piece? What a ridiculous question. It's not even, they don't even touch. It's not part, it seems a bunch of nonsense, right? Let me again remind you, we'll go back to this business here, right? Thinking about now the fundamental theorem of calculus. How much of the change that we see on the boundary here, we measure change on the boundary, but no one's walking around thinking the change happened on the boundary just because we compute it on the boundary. No, of course not. Don't be silly. Where the change actually happens is obviously, right, it's these values of x right there. It's literally in the interior that it happens, even though we measure it on the boundary. And again, harder to visualize in this situation here, but it's an accumulating quantity. And so even though it's a little harder to visualize, it's the same punchline. We detect flux on the boundary. The formula, yes, is computed on the boundary, but it's happening in the interior. And I have some physical examples that I'm going to show you whenever we have time. I probably won't get to it today. But I do have some physical examples that really literally bring this out. So, accumulating quantity. It's a kind of a stuff. It's distributed over the interior. Whoa, what did I just do there? I was in the wrong. Okay. Accumulating quantity. It behaves like a stuff. And there is an associated density. Now, where these formulas came from is a long discussion that is very important, but in terms of the payoff, the actual computation of this formula, I just don't think it pays off in a time-tight situation like we have, right? So just like with Green's theorem, recall I never showed you the derivation of the formula for Green's operator. I just wrote it down, right? And we're going to do the same thing here. It's not such a big deal to motivate it, but it is I'm just going to call it kind of a tedious calculation. So here's the formula. In the same sense that mass density is mass per unit volume, and with the understanding that likewise we're going to define flux density to be flux per unit volume, again viewing it as a stuff distributed over the interior. here's the formula. Flux density, the thing that you multiply by dV to get d phi, computed by that formula right there, which of course you all recognize. That's divergence. We saw that in Chapter 3. We didn't have any context in Chapter 3. Right? Wasn't clear why this was something that would be interesting or what I would be doing with this expression, other than a vague reference to, it's talking about how the fluid's kind of flowing outward. But anyway, that is now, you can see the context. It is literally a way of computing flux. In other words, how much outward through the boundary flux, and therefore how much is the fluid flowing in this outward way per unit volume. And that's the motivation to interpret divergence as it's computing this kind of outward, to the extent to which the fluid is flowing outward away from some given region. Let me pause on that for real quick. Everybody buying that? Okay. So let's see here. Flux density, we talked about. This is what it's called. This is what you can do with it. This is how you compute it. This is the other term that you can call it. By the way, I'll remind you, in my physics classes, I heard the term flux density more often than I heard the term divergence, right? Mathematicians will usually call this divergence. My experience, decades out of date, though I'll confess it is, my experience was that flux density was the more common term in physics, and I would speculate maybe also in engineering. And then we have these notations, and we talked about these notations previously when we were talking about divergence in Chapter 3. And again, del dot, very common. It's, a little math slang, right? A little bit of, a little uncomfortable in a certain way, but very standard, very convenient, very standard. All over the place you're going to see it. You might as well jump on board. Very common choice. Okay. All right. Now, before I kind of already talked about that. Before we put it all together, let me just remind you that when I say that divergence is flux density, it's literally telling you, right, how much of the flux is actually happening in the vicinity of a given little piece of volume. It's literally playing that role. And here's that interpretation in action. We have here a vector field. This vector field creates a flux through whatever surface you're looking at, your boundary surface, that is. Where is that flux coming from? We already agreed it's coming from the interior. Okay, well, where in the interior? And for example, if I were to look at these 2 points here, is there more flux coming from the A point or from the B point? And okay, well, the way we answer this is, since we're talking about a flux, then here's the corresponding flux density. It's divergence. Again, divergence is something we have a formula for. You can just straight up compute it. You can then plug in the 2 points and then just see which one's bigger. And 75 is bigger than 48. I hope I did the arithmetic. That's the bigger one. That's where there's more flux density. That means this point here, B, is where more flux is coming from as compared to A. What do you think? Everybody good? All right. So, putting it all together. We agreed that flux was an accumulating quantity. Holds the sum of the parts. We talked about how on any little part, because it's an accumulating quantity, there's a corresponding notion of density, and we know what that density is. The density was divergence. And so flux per unit volume is the divergence. And then recalling, right, that the whole reason we were interested in flux in the first place, or let me say that differently, our explicit formula for how to compute flux in the first place was this surface integral, and so altogether we have ourselves a new theorem that boundary surface integrals, boundary fluxes, can be computed as triple integrals of divergence over the interior. And this is called Gauss's divergence theorem. Everybody buying it? Okay. And I think just for dramatic purposes, again, let's just to compare, recall that this is morally pretty much the argument that we wrote down over here when we wrote down Green's theorem, right? We said, well, it's an accumulating quantity, and there's an associated density, and the density itself was, well, in that case, it was curl. Over here, it's different density for different quantities. No surprise. But structurally, again, you see the argument is it's the same. It's morally the exact same basic idea. Okay. Yeah. Okay. So let's do one. How am I doing on time? Okay. Well, it was good. Okay, so this example right here, we're going to blah, blah, blah set up, but you see it says compute the flux. Our theorem is about flux. Cool, let's plan to make use of this, but notice a very, very important worry, and you've got to be careful about this. I made a huge deal out of this when we were talking about Green's theorem with its first example. Specifically, Gauss's theorem here does not just compute any old flux you might feel like. It says so right here. It only works for boundaries. That was critical to how the argument played out. Right? The reason this whole thing worked was because of the fact that we were looking at boundaries. It's only because it's boundaries that I can talk about, comparing the surface, which is a boundary, to an interior, and the whole being the sum of the parts. It only works if it's boundaries. So we have to ask, is the surface that we've been given here, is it a boundary? Right? And again, you cannot just go around applying Gauss's theorem willy-nilly to any flux integral that you might want to compute. It's wildly inappropriate. It will not work. It's a bunch of garbage nonsense unless you have established that your surface is a boundary. So let's look now with that worry in mind. Let's look at this question. Our surface here, let's see here, our surface is the inward-oriented unit sphere. Okay, there's the unit sphere. There's inward-oriented. That's what our surface S is. And is that a boundary? Oh, man, no, it's not. Boundary, again, is a loaded word. Boundary means oriented according to these very rigid, standard, arbitrary, but standard interpretations of what we mean by orientation. And that's not it. So we cannot, as it stands right here, we cannot apply Gauss's divergence theorem. So what we're going to do, and I'm going to bail for today, but what we're going to do is we're going to play a little fast one where we think about a different, importantly different surface called S minus. We're going to observe that that is a boundary. We're going to account for the fact that we're looking at the wrong surface appropriately, blah, 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 and you can see it's all going to work out very nicely. Okay, so I'm going to draw the line then right here, and we will pick up here on tomorrow. Okay, see y'all later. Have a good one.